So in this video, we're going to review what to do after the rejection of the null hypothesis with the analysis of variance procedure. Now, recall that not every research study will result in a statistically significant result where we reject the null hypothesis, and if that's the case, that's where it would stop. But in our example, we did reject the null hypothesis, requiring us to conduct a post hoc procedure. Now, the term post hoc generally refers to occurring after the event. Of course, the event in this case is the ANOVA procedure. And so because of that, we can refer to the ANOVA procedure as a confirmatory test. And what we're essentially doing is confirming if we will reject the null hypothesis, causing us to consider an alternative to that, or we do not reject the null hypothesis. But in our example, we did reject the null hypothesis. Another term to describe this confirmatory test is the omnibus F test. And omnibus is referring to the overall examination of whether there are potentially significant differences among the levels of our factor. Of course, our factor was business sector, and we had 5 levels. Now, the post hoc procedure, comparably to the ANOVA procedure, is referred to as an exploratory test. So what we're doing here is we're going in to explore where those differences exist. And once again, this is performed after the ANOVA in the event that the obtained F statistic exceeds or is at least as large as the critical F value. And so we're going to explore where those differences exist between those groups. Another term for the post hoc procedure is multiple comparison procedure, because that's essentially what we're doing is we're going to make comparisons pairwise between the different groups in a way that does not inflate the risk of committing a type 1 error. And what you see in this box are a range of different multiple comparison or post hoc procedures named after various statisticians that developed these procedures. And the one at the top, Fisher's least significance difference, is a mathematical approach or statistical approach that is more likely to find significant differences inside those 5 groups. On the far other end, the Chaffee comparison is a statistical procedure that is less likely to find significant differences among those 5 groups. And so when we take a look at this list here, the Fishers all the way through the Chaffee comparison, these are said to be more conservative, indicating that at the bottom of this list, these are statistical procedures that have a greater degree of rigor to them, in that it requires a higher standard to say that these 2 comparisons, or this one comparison of the 2 groups, is statistically significant. Alternatively, as we go from the bottom to the top, we find that we are more liberal in that the Fisher least significant difference is the least rigorous and is more likely to find differences among those pairs. So the more common test that's used is somewhere in the middle, and that's the Tukey post hoc procedure. And this is the one I'll demonstrate here in this video. So to carry out the Tukey post hoc procedure, it is a very popular, probably the most popular post hoc procedure used in various lines of research, and requires the calculation of a new critical value. And so to do these calculations, we need to draw some information. We need the degrees of freedom from the mean square within term. We need to determine an alpha level, and usually, unless it's stated otherwise, we always go with 0.05. So we need the number of cases per group, and remember we had 7 per group. And once again, we need, just to reiterate, we need the degrees of freedom for the within term or the error term. Those terms are used interchangeably. And now we look up a new critical value, and that's called the Q value from the Q table. And this requires us to state a new null hypothesis. And this null hypothesis states that the comparisons that we'll make, and we do them pairwise at a time, so I will refer to one group, J will refer to another group, that there will not be any differences compared to the alternative, which we state that there will be a difference. It will not be equal. So we always go non-directional on the post hoc procedure. We're going to select the significance level of 0.05 unless stated otherwise. We use the 0.05. We had 7 cases per group. Recall that our mean square within term was 1.59, so we're going to carry forward with that. And our degrees of freedom error term, for the error term, was 30. And this becomes our new test statistic, the Tukey HSD value, which is equal to the Q value at a given alpha level, and so our alpha level is 0.05, and this is what we get from the Q table. And we multiply that by the square root of the ratio of the mean square within term, which was the 1.59, divided by the number of cases per group, and in this case we had 7. So what we need here is that Q value. So the terms inside the square root symbol were obtained from our previous analysis. So what we're looking at here on this slide is an excerpt of the Q table, and along the top what we're looking for are the number of means, or the number of groups in our analysis. And recall we had 5 groups. Along the column here on the far left hand side, we're going to look for the degrees of freedom for the error term, and note we have 30, and this table presents Q values if we want to go with the 0.05 or 0.01, and we're going with the 0.05, and we look for the value of intersection, and that zeroes in on a Q value of 4.10. So this is the value we need to extract from the table and put into our equation. So once again, we have our Tukey HSD equation, and by substituting our values, we have the 4.10, which we got from the table, and the mean square within was 1.59 divided by the number of cases per group, which was 7. Running the calculation, we have a Tukey value of 1.954, and this is what we're going to use to examine differences between the individual pairs inside our 5 groups. And so the rule here, if the absolute value of any comparison is at least this large or greater, then we reject the null hypothesis for that comparison. If the absolute value is less, then we do not reject. We would state that those 2 groups are not statistically different. So once we have our Tukey value, we're now ready to move forward with the actual comparisons. And we do this in a table where we zero in on the group average. So once we've generated our descriptive statistics, then we go back to our descriptives and we pull up the average for each group. You'll notice along the top I have the group numbers here, but these are not in numerical order by the group assignment. These are in ascending order from the smallest average all the way up to the largest average. And then along the column here, we would list the groups in the exact same way, from the smallest average up to the greatest average in that ascending order. Now, what we do inside the cells is we just take the absolute value of the difference. So what we did here with group 3, 5 subtract 4.43 is 0.57. So the order of the subtraction doesn't matter here. Even if we get a negative, we just put the absolute value inside the cells. So 5.29 subtract 4.43 is 0.86. Of course, 4.43 subtract 4.43 is 0, so we don't even put the 0 here. We just put the dotted lines indicating that we don't compare one group to the other. But this is a handy way to summarize pairwise differences. And so what we see here is that we're conducting a pair-by-pair comparison by looking at the difference in the group averages. And once we've completed our table, you'll notice that these cells here are blank at the bottom because these would be a mirror image of what we have along the top of our diagonal. So we don't have to redo this on the bottom. We can just do one side. And what we're looking for are values and compare those values to our Tukey critical value that we had calculated on slide 22. So using our critical value of 1.954, we're going to go through and we look for the differences between these pairs of groups that is at least this large. And what we do is what we find is that we zero in on these three cells right here. You'll notice 1.86 gets pretty close to 1.954, but it's still not at least as large as 1.954, so we would not flag this one right here. But we see that the comparison between group 2 and group 5, group 2 and group 3, group 2 and group 1, the differences exceed the 1.954. So we would conclude that there is a statistically significant difference between groups 2 and 5, group 2 and 3, group 2 and group 1. So what we see here, we would conclude that group 2 was significantly different than groups 1, 3, and 5. Now, you could present the descriptive data in a table as we already had, but very often presenting the data graphically is much more powerful in illustrating where those differences reside. So what we see here along the x-axis, I indicate the business sector, and I ordered the business sector according to the group number that they were assigned, and along the y-axis is the dependent variable, which are the number of new outlets that were open. So the bar height represents the average for each of those 5 groups, and the error bars represent the standard deviations for each of those 5 groups. And there are a couple of different ways in doing this, but as the researcher here, I decided to indicate this by group assignment. So now, in terms of our statistical analysis, we have to interpret the data, and the asterisks here indicate that these would be significantly different than the cannabis. So what we see here is that cannabis stores open statistically more outlets, or the cannabis business opened statistically more outlets in 2023 than hardware, convenience stores, and restaurants. And that is done, we can make that conclusion accepting the fact that we could be making a type 1 error, but that risk of committing a type 1 error is at least less than 5%. So this ends our final video on the ANOVA procedure.